Yes.
Okay, now from this last time we already did 6.3, I give you reminded you with the basic identities that B1, B2, B3, B4 with the numbering, right? And now, last time I asked you to memorize this set of identities. We start with group 1, right? Now, I hope you already watched the lecture video where I derived these formulas. It's actually fun. It's actually fun and nice to know how the proof was done. And my personal experience is that since I first saw those formulas until now, I memorized those. I think it's because my teacher actually showed me the proof that I knew how this formula being derived and came up. Okay, so I'm not saying that I'm so smart that I memorized it for like 20 something years. Actually, how many years? Almost 30 years. I learned that in my middle school. But no, it's not because me being smart. It's because the method of teaching. Okay, so the instructor show you the proof so that you can internalize how the formula actually comes up. Okay, but because of time, I will not go over those proofs anymore, and it's already there in your lecture video. Okay, I will just show you here how to use these formulas. Okay, now let's start with some problems in our 6.3. Let's do, for example, number 5b. Oh, okay. You know what? Let me do 5a and 5b so that you can see the contrast. Now, 5a, we have cosine pi over 4. I have a habit that if the angle is with fractions like that, I put parentheses. Why? Because, of course, for example, cosine pi over 4 is not the same to cosine pi over 4. You know, sometimes you just say, oh, this is just a slip of writing, right? I meant a pi over 4 times. But well, you write what you mean what you write, right? You cannot say it's just a slip of writing. Okay, it's not the same to slip of tongue. Slip of tongue, can't really see your mistake. Okay, but slip of writing, you can see it, but you still leave it there. Okay, now cosine pi over 4, that's cosine 45 degree, radical 2 over 2, while cosine pi is -1 divided by 4. So you see that they are different. In fact, one of them positive, the other one is negative. Okay, now that's why so will I be wrong, Thomas, if I write my angle cosine pi over 4 like this? No, it's not wrong. It's not wrong. But make sure this horizontal line for the fraction is actually hitting the middle of cosine. You don't want to write it this way, however innocent it looks like, right? But trust me, it's just about time, then this line will get longer and longer and longer and longer. And suddenly we all believe in evolution. Right? Some people believe that, some people don't. It's not my issue here. But like, you see, even in math, in your handwriting, right? You don't take thousands of years for this to change, right? You just take a couple minutes. Why? Because it starts from wrong writing. Okay. Now, to avoid that misunderstanding, so I put parentheses to emphasize that's the angle inside the cosine. Okay, that's we call that the argument. Okay, yeah, that's me now, and I think you may want to follow that view also. Just to, it's like we try to be careful not to make further mistakes. Okay, so do I need to use parentheses there? No, as long as you write it properly, it's okay. Okay, but it is possible that when we write things too fast, then we end up missing some details and incorrectly write it. Okay, I call that slip of writing instead of slip of tongue or slip of hands, whatever you call it. This is radical 2 over 2 plus this is radical 3 over 2. Therefore, this is radical 2 plus radical 3 over 2. Okay. Definitely greater than 1. Okay, why? Because this is greater than 1/2. This is also greater than 1/2. When you add them, of course, should be greater than 1. Okay, in this case. In this case. However, if you contrast that with part B, cosine of 5 pi over 12, which is cosine of 3 pi over 12 and 2 pi over 12, which is cosine 3 pi over 12 is pi over 4 plus pi over 6. Now, then we will use formula 1, cosine of sum. This becomes cosine pi over 4 times cosine pi over 6 minus sine pi over 4 sine pi over 6. This is radical 2 over 4. I'm sorry, radical 2 over 2 times radical 3 over 2 minus radical 2 over 2 times sine pi over 6, sine 30 degrees, that's 1/2. This becomes radical 6 over 4 minus radical 2 over 4. Okay, now this is less than 1, right? Okay, minus something less than 1. The difference must be less than 1. Okay, so at least from this point of view, we know we can do a fast view that cosine A plus B is not equals to cosine A plus cosine B. Okay, it's not. From here we can see. Okay. If they are the same, what's the point of us having this formula up here? Right? Okay. If they are the same, then why do we need this formula? No, just use cosine A plus cosine B. But no, they are not the same. That's why. Okay, they are not the same. Now, let me go on. So that's one example of the use of those formulas. Now, most of the time, what you really need actually, not only memorizing the formulas forward, like how to use the formula, but more importantly, you recognize backward. In other words, if you see these, can you go back there? When you see these, can you go back here? That's actually more important. Okay, so I will do a couple more problems on how to compute. Okay, let's say number 9b. Number 9b, what is sine pi over 12? Or this is sine 15 degrees, by the way. Okay, now 15 degrees. For 15 degrees, you can break it up as 60 minus 45 or 45 minus 30, either one. Okay, now our textbook gives us the hint, use pi over 12 as pi over 4 minus pi over 6. So basically 3 pi over, sorry, not 3 pi, is, that's right, 3 pi, what do I want to use? Pi over 6 then. Pi over 6 at 2 pi over 6 minus pi over 4. So that's 3 pi over 12, 4 pi over 12. That's one way, or yeah, pi over 3. Yeah, pi over 3 is 4 pi. I want to show you the denominator 12. Or you can also use sine 3 pi over 12 minus 2 pi over 12. Right? This is the 60 degrees minus 45 degrees. This one is 45 degrees minus 30 degrees. Okay, there are two different ways to approach this, and you will get the same result. Okay, you will get the same result. Okay, let me rewrite this as sine pi over 3 minus pi over 4. Okay, our textbook actually give you the hint for this one. This is textbook. Again, that will be the same. That will be the same. Okay, you can use either one. Then I use this is formula 1,4, right? Sine A cosine B minus cosine A sine B. Okay. Now, the structure is pretty much like this. 1, 2, those both are cosine sum difference. Cosine sum difference. 3, 4 are sine sum difference. 5, 6 is tangent sum difference. Tangent sum difference. Okay, now for the cosine, it's negative first and then plus. For sine, it follows the sign, the plus and then minus. For tangent, because it follows sine over cosine, there will be plus minus. You see? Okay, now for cosine, it's cosine, cosine, sine, sine. Cosine, cosine, sine, sine. Sine, cosine, cosine, sine. Sine, cosine, cosine, sine. And then you have tangent plus tangent, tangent minus tangent, you know, okay, and so on and so forth. So think of that as this kind of pattern, okay? Basically do everything possible to memorize this as fast as possible. Create some mnemonic, whatever, okay, whatever you need to memorize them well and fast, okay? Now then, sine pi over 3 radical 3 over 2, cosine pi over 4 is radical 2 over 2, cosine pi over 3 is 1/2, this is radical 2 over 2, I get radical 6 over 4 minus radical 2 over 4, that's radical 6 minus radical 2 over 4. Okay. Oh, Thomas, don't you think it's kind of strange why the answer from 9b is the same to the answer for number 5b? Okay, so just little note. For 9b, we have sine pi over 12. Okay. Can we explain why cosine pi over 12 is the same to sine pi over 12 is the same to cosine 5 pi over 12? Well, because they are actually complementary angles. Remember? Right? Pi over 12 plus 5 pi over 12 equals to 6 pi over 12, which is pi over 2. Remember that? Okay, the cofunctions. B3, 1. If two angles are complementary, then cosine of one of them equals to, sine of one of them is equals to cosine of the other one. Okay, now let's go on. the one that I said that you need to memorize, right? You need to memorize backward. Like for example, number 11, cosine 70 degrees, cosine 53 degrees, plus sine 70 degrees, sine 53 degrees. Okay, now instead of computing them one by one, and then multiply and then add, so it involves so much rounding error, you see, oh, this is actually formula 1, 2, which is cosine of difference. So this is equals to cosine 17 degrees. And from there, if you want to compute that, go ahead. Use your calculator after that, if you need to compute it, okay? Yeah, but if you compute using calculator, this one, you already have 5 decimal places. So you already do rounding, right? And another one here, you already do rounding, rounding, rounding. You already have four roundings in just plugging numbers. Okay, not to say that when you multiply this, that's rounding number 5, this is rounding number 6. And then when you add them, you have rounding number 7. You have compounded rounding errors. Okay, no wonder at the end, the number you get, if you compute them one by one, you have too much rounding error. Okay. Now that's for number 11. Let's see number. So imagine if I ask you this question, for example, find the exact value. This is my own question. Find the exact value of sine 53 degrees, cosine 7 degrees, plus cosine 53 degrees, sine 7 degrees. Now, what you need to avoid doing is using calculator, okay? If you notice, this is formula 1, 3, right? This is sine 53 degrees plus 7 degrees, which is sine 60 degrees, which is a special angle. Then we can get the exact value. You see that? Okay. Which will not be achieved if you use calculator right away here. Now, the thing is, sine, cosine, tangent, cotangent, secant, cosecant are so closely related such that moving forward, you will see that once you do rounding in one of them, you will never get exact value back anymore. Okay, now, more importantly, let's go on to, let's say, number 17. Sine alpha equals to -5/13, and tangent alpha is positive. Now from here we see alpha is in which quadrant? Can you tell? Sine is negative, tangent positive. What quadrant is that? That's quadrant 3, right? Okay, that's quadrant 3. Now then, the question here is, what is sine alpha minus pi minus 3? Okay, that's the question. Let's set it up first. Let's set it up. Okay, sine alpha minus pi over 3 means I need sine alpha. This will be sine alpha cosine pi over 3 minus cosine alpha sine pi over 3, right? I will need that. Now the thing is, we memorize the value for this. This is already given, but I need to find this out. Okay, I need to find it out. So I still need to go back to the drawing board. Okay, so if sine alpha is negative 5/13. Draw the triangle for the reference angle. This is alpha hat, the reference angle. Sine 5/13. Positive, right? Okay, let me write it down. Sine alpha hat is 5/13. Then you come up with that right triangle. Now, what is the adjacent? That's 12, right? So cosine alpha hat is 12/13. Now go back to cosine alpha, the angle in quadrant 3. Cosine alpha, it must be the same number, but this time, because it's in quadrant 3, it must be negative. Okay, now we go back to what we need to answer. What is sine alpha minus pi/3? That is sine alpha cosine pi/3 minus cosine alpha sine pi/3. That is equals to negative 5/13. Cosine pi/3 is 1/2 minus cosine alpha is negative 12/13. Sine pi/3 is radical 3/2. So this will be negative 5/26 plus 12 radical 3/26. Put them together, it's negative 5 plus 12 radical 3/26. That's the exact value. Okay. Number 23. Let me do it here. Number 23. And I usually have this kind of question in my test though. Okay, number 23. It says that cosine alpha is 4/5. Alpha is in quadrant 1. It is, they say it's acute angle, so it must be quadrant 1. Okay. And then tangent beta is 5/12. Beta also in quadrant 1. So they are nice, both of them in quadrant 1. Oh, actually, this is 8/15. Yeah, both of them in quadrant 1. So you can draw the triangle right away, right? You can draw the triangle right away. If this is alpha, cosine 4/5 by Pythagorean triplet, that must be 3. For beta, tangent beta is 8/15 by Pythagorean triples. This is 17. And both of them are alpha and beta already, not reference angle. So we can safely say we get all sine, cosine, tangent of these both triangles, both angles alpha and beta. So part A, what is sine alpha plus beta? Part A, what is sine alpha plus beta? This will be sine alpha cosine beta plus cosine alpha sine beta. Write down the formula first as always, okay? And then you plug in numbers. Sine alpha is 3/5. Cosine beta is 15/17. Cosine alpha is 4/5. Sine beta is 8/17. Now we want to keep LCD. That's why I will not cross cancel whenever possible. Like you may think, oh, Thomas, can I just cancel this? You can, but Simply because you can do it doesn't mean you have to do it. Okay, yeah, you can, but no, I will not. Why? Because I want to maintain the LCD 85. Okay, so I get 77 over 85. Now part B, how about the cosine alpha plus beta? Cosine alpha plus beta. This is cosine alpha, cosine beta, minus sine alpha, sine beta. Oh, Thomas, why is it minus here? While this is plus. Now, honestly, if you have that question, the only way I can say that is like go back to the formula. Okay, so in the end, it's about do you memorize the formula? Okay, if you don't memorize the formula, then go back, memorize that first. Okay, because otherwise, then we'll argue a lot. But Thomas, when sine, it is positive. When sine is positive, why when cosine is negative? Is it a form of discrimination against cosine? No. It's the formula is just like that. There's a we derive that formula. Okay, we derive that formula. It's not that we treat them differently. Okay, instead we treat them the same way with all the backgrounds such that we get such result. Okay. After all, since the beginning, we know sine is increasing in quadrant 1 and cosine is decreasing in quadrant 1. Okay, so the nature of sine and cosine itself already different. Okay, now cosine alpha is 4/5. Cosine beta is 5 over 17 minus sine alpha is 3/5. Sine beta is 8 over 17. That is 45 minus 24 over 85. That is 21 over 85. Okay. Now, we see that the follow-up question, actually, part C, then angle alpha plus beta is in which quadrant? Alpha plus beta is in quadrant what? The way we see is sine of that angle is positive, cosine of the same angle is also positive. So that angle must be in quadrant 1. Why? Because sine of alpha plus beta, cosine alpha plus beta of the same angle are both positive. Okay, now almost every time I teach this part, it reminds me to your diploma. Okay, so what I'm about to say right now, actually not part of your study, but part of your personal growth. Okay, it is not about what alpha plus beta are. In fact, we solve this problem here without knowing what are alpha plus beta themselves, alpha and beta themselves, what the angle actually are. Okay, but it's not about who they are, it's about what they do. Okay, now when I say it that way, it sounds like okay, so what it has to do with me, Thomas? That's actually one of my philosophy. It's not about who I am, like who are my parents, where I'm from, what kind of language I speak, how much money I make. No. Okay, what kind of house I have, what kind of car I have. No, it's not about who we are, but what we do. Okay, in fact, I think one of my pastor kept reminding us it's about what you do that people know who you are. Okay, if doesn't matter who you are, if you do nothing, then you are basically useless. Okay, what you do tells other people who you are. Okay, now Why I relate that to your diploma? Because of this. Oops, I'm sorry. Oh, shoot. It gets recorded. I'm sorry. I'm so sorry. Oh, shoot. Hold on. No, is it? Did you see that? No, I don't think so. Hold on. This is not recorded. No. Okay, good. Okay, let me change. I thought that it happens to be recorded. Give me a second. Because the page I get into is your grades actually. Hold on. Okay, what I want to show you is this. Okay. I want to show you Indonesian money. This is Indonesian money. Put it back to our notes so that we can see together even better. Okay, and write on it. This is Indonesian money. And of course, you may find it to be strange that Indonesia have this. Hold on, I want to enlarge this. How to enlarge this? Yeah, I want to enlarge this. Indonesia have this 75,000 bill. It's kind of strange number, huh? Okay, but that's actually very creative. This bill, this one here, is to commemorate the 75th anniversary of Indonesia's independence. So we have that last year. Yeah, they pull it out. Okay, even though this is a legal tender, but nobody actually used that. Why? Because for you to get this bill, the 75,000, you need to order it. You need to order it from the government. Basically, the effort, you need to pay how much to get this bill? You need to pay 75,000 Indonesian dollar, 75,000 Indonesian dollar to get this bill. So you don't lose anything, but the effort is a lot more because you need to fill this form, you need to fill that form, you need to submit it here, submit it there, and then transfer the money to government, this and that. Then you need to wait for 1 month for you to get that bill. Basically, maybe not 1 month, maybe only 2 weeks. But basically, it's a lot of effort to get this 75,000 Indonesian dollar bill. Okay, so nobody actually used that as a legal tender. If people try to sell it on the market, people actually sell it for 10 times the face value. Okay, now that's for the one. But for the others, you see that this number here. How about this one here? How about this one here? 1,000 Indonesian dollar. Don't you think that's a very big money, right? Okay. One way I make students happy in the past was like every time I go back to Indonesia, I brought like 1,000 Indonesian dollar, 5,000 Indonesian dollar, and if somebody get an A, I give that person 5,000 Indonesian dollar. At least it makes them feel very rich. If they get a B, I give them 2,000 Indonesian dollar. Okay, and of course there were some kids that I give them 1,000 Indonesian dollar. They are so happy. They are much more happier when I give them 1,000 Indonesian dollar compared to 10 US dollar. Because of course they have hard time to get that, right? Especially the new crispy Indonesian money. But I want you to realize that let's go back to here. You know, go to finance and take a look here. This is the conversion, Indonesian money, American to Indonesian money. Screenshot that. Bring back to our notes. And put it here. Give me a second. This is the conversion rate. Now, if you are international students, well, you know what I'm talking about here. Okay, you see that our $1 actually worth more than Indonesian $10,000. Do you see that? $1 worth more than Indonesian $10,000. Now, I'm not talking shit about Indonesia. I'm from Indonesia. Okay, no, it's not about that. What I'm trying to say is your diploma may look the same. Your diploma may show whatever kind of degrees, but the value is actually less than other diploma. And you know what it means? You're wasting your time. What's the point of getting this kind of diploma? I'm not saying that this is worth nothing. No, but this can be your diploma. Your diploma can show a PhD in whatever. Okay, but nothing you can buy with that diploma. Nothing you cannot generate a good income for your family and put food on the table with that diploma. What for? Okay, it's not about who you are. It's about what you do. It's not about how many zeros you have on your diploma. It's about what you can do with that diploma. Okay, so you can see here that the largest bill in Indonesian currency is 100,000 Indonesian dollar. This one here. This one here. But do you realize that this is actually worth less than $10? It's worth less than $10. It's approximately only $7. Okay, so the feeling of having $10 in your wallet, $10 in your wallet, is much higher. It can do much more with $10 than 100,000 Indonesian dollar. Now go back to your diploma. Your diploma can have a PhD in whatever study. And then you may graduate from a very good university, call that Harvard, MIT. Okay. And it makes you so proud of your PhD, right? But the next question is, what do you do? Okay? It's not about what degree you have, that's who you are, but what do you do? Well, I'm still looking for jobs there. Okay, so it seems like your PhD is worthless, that nobody demanded. What for? Right? Why don't you take classes, okay, get degrees that is demanded, right? Okay. Well, Thomas, so I can solve a lot of problems. Well, apparently nobody's going to pay you to solve those problems. So what's the point? Okay, so please don't worry about your GPA too much. Okay, worry about what you can do later on. And unfortunately, I'm that kind of instructor. Okay, I'm that kind of instructor. I'm the kind of instructor who wants you to be able to sell your skill. Okay, so I need to provide you the skill. You may say, Thomas, what you teach me here is something I cannot sell. Well, but I can with this. You can go to calculus class and perform well there. Okay, that's what I try to I promise you when I pass you. Okay, it's instead of just passing you and then call that success. No, the best way to see if I'm a successful teacher is how you fare, how you do in the next class with another instructor. Okay, that's actually the best way to see that. Okay, so not about hey, you know what, I have this kind of degree that now it doesn't matter. It's not about what alpha and beta are. it's what they behave, how they behave. The sine is positive, the cosine is positive, so that angle must be in quadrant 1. Okay, now we will do one more problem like this, a similar problem. Oops, I go too far. We'll do one more problem like this, and then we move on to other type of question. Okay, let's say I take number 27. Number 27. So cosine alpha is negative 2/5. Cosine beta is negative 3/5. Both of them in quadrant 3. Now, so suppose the main question later on is, so let's say the main question later on is of which quadrant A minus B is A minus B located. Okay, now most students actually did the inverse cosine in these both cases. That's actually a wrong way to do it. Okay, don't use inverse cosine. Okay, don't use inverse cosine. We have not learned in detail what is cosine inverse doing. Okay, but I can tell you that's a wrong way to do it. Okay, no, that's not how you do it. That's not how you do it. Okay, the better way to do it, the correct way to do it is to see how sine and cosine, or with tangent instead, behave like the plus or minus of this alpha minus beta. Okay, so the way we do it will be, you see that even though they ask what is sine alpha minus beta, cosine alpha minus beta, but the main question is actually which quadrant it is located. Okay, if you look at that number 27 again, that's the main question. Part C is the main question. Most students think that A and B are the questions. No, no. Actually, A and B leads you to part C, which is the main question. Now, so to answer this question, we start with sine alpha minus beta. It's not who it is, it's about how they behave. Okay, put it under sine, what happened? Okay, and then after that, you put it under cosine, see what happened. Is it positive or negative? Okay, how do we know somebody is faithful? Put that person under temptation. How do we know somebody is a hard worker? Give that person hard work. Okay, to be honest with you, I have heard students saying, oh, Thomas, I'm a good student. Okay, so what? It's about who you are, but it's not what you do, right? And the claim that I am a good student, do you believe it or not? It's something everybody can say, right? You and I, everybody else can say the same thing. Doesn't make you a good student. Okay. I heard that song for more than 20 years. Thomas, I'm a good student. Okay. I just don't have time to study. Oh, no, that's contradiction to the first sentence. Okay. If you're a good student, then you should have a good time management. And that's implied. You cannot say I'm a good student, but that I don't study. It's just like I'm a good husband, I just cheat. No, come on. Okay, that's contradiction. Okay, Now, so we will see how sine alpha minus beta and cosine alpha minus beta, are they positive, negative? And then from there, we can decide which quadrant they are located. But for us to have this done, we need to first set up the triangle. The thing is, both of these angles are not in quadrant 1. So I need to talk about the reference angle first, and then draw the triangle. Does it make sense? Okay, this is 2, this is 5, then this is square root of 21, right? 25 minus 4. Now for cosine beta, that's negative 3/5. So the reference angle, cosine of the reference angle will be positive 3/5. Okay. Reference angle always quadrant 1, and therefore the value of trig functions always positive. Okay, this is 3, this is 5, 25 minus, oh, this is 4, duh. Okay, now from there, then we see sine alpha hat will be radical 21 over 5, and therefore sine alpha, the one in quadrant 3, will be negative. Likewise, sine beta hat is 4/5. Therefore, sine beta, the one in quadrant 3, will be negative 4/5. Now, we are ready to attack A and B. That's sine alpha cosine beta minus cosine alpha sine beta. Okay, sine alpha is negative square root of 21 over 5. Cosine beta is, that's given, negative 3/5. Minus cosine alpha is negative 2/5 times sine beta, negative 4/5. This is positive 3 square root of 21 minus 8 over 25. Okay, is it positive or negative, by the way? Can you tell? Without using calculator, can you tell? Is 3 square root of 21 minus 8 positive or negative? Can you tell? Now, square root of 21 is greater than square root of 16, right? Now, 3 times square root of 16, that's 12. So it must be positive. Does it make sense? So this is positive. See, I do that without calculator. You can use calculator if you want, okay? Because the question is it positive or negative? Just use your calculator. Okay? Let's approximate anyway. You just need that to be positive or negative, right? But I mean, since you are in calculus already, do you have that intuition to compute, just to realize it's positive or negative without using calculator? This is cosine alpha cosine beta plus sine alpha sine beta. Cosine alpha negative 2/5, cosine beta negative 3/5 plus sine alpha negative square root of 21 over 5. Sine beta is negative 4/5. Oh, this is positive. This is 6 plus 4 square root of 21 over 25. Okay, this is definitely positive. So part C is alpha minus beta is in quadrant 1 because I don't need to know who you are. I just need to know what you do. From there, I know who you are. Okay, because sine of that angle is positive, and cosine of that angle is also positive. In fact, then from there we can say, so actually, because it's in quadrant 1, then alpha must be greater than beta, right? Okay, by the way, that's just extra few, right? Okay, and it's in quadrant 1, so alpha is greater than beta. Okay. That's for number 27. Let me do one more problem and then I take a break. But this time, how about proving? Number 49. Number 49, proof the identity 1 over cotangent alpha minus cotangent beta equals to sine alpha sine beta over sine beta minus alpha. Again, to prove, you can go from left to right, you can go from right to left. Okay, either one, but we see which is more complicated. Now, the thing is, we have the formula for this, don't we? Right? So what we can do later on, I will break this up and then go on from there later on. So instead of going from left to right, I will go from right to left. So let's do right to left. Right hand side is equal to, if you want to save some space, instead of writing the right hand side here, it is okay for you to write next line. Okay, just remember that your equal sign is supposed to be straight. Okay, so right hand side will be sine alpha sine beta big over sine beta minus alpha. That's actually part of the first line that I make into the second line. Now then, I will use formula 1,3 to expand sine beta minus alpha. Sine beta cosine alpha minus cosine beta sine alpha. Is it okay? Now the thing is, our main goal is to have 1 on the top. So this is supposed to be 1. How do I make it to be 1? Divide by itself. So I will divide the top and the bottom by sine alpha sine beta. Basically, then it will look like this. There will be sine alpha sine beta over sine alpha sine beta big over sine beta cosine alpha over sine alpha sine beta minus the bottom right cosine beta sine alpha also divided by sine alpha sine beta. Okay, so this guy is here, this guy is here, this guy is here. Each one of them divided by sine alpha sine beta. Now you see then, of course, on the top, as we expected, that becomes 1 on the top. What happened on the bottom left? Sine beta cancel. right? So we have cosine alpha over sine alpha, and the bottom right, sine alpha cancels. We end up with cosine beta over sine beta. But that is cotangent alpha on the bottom left, cotangent beta in the bottom right, which is what we have on the left-hand side. Okay, that's what we have on the left-hand side. But Thomas, can I go from right to left? You can try. Okay, I just don't think that on the left-hand side is more complicated though, but doesn't mean it's not doable. Okay, it doesn't mean it's not doable. In fact, let's try to do that. Why not? Okay, so suppose alternatively, I do from right to left. Now, I'm not showing you this to confuse you. I'm showing you this to remind you that proofs are not unique, but you still need to show the same structure. Okay, suppose I start from left-hand side, which is 1 over cotangent alpha minus cotangent beta. This is 1 over cosine alpha over sine alpha minus cosine beta over sine beta. Then multiply the top and the bottom by the LCD, sine alpha sine beta. And that's actually a common practice. If you have complex fractions, multiply by the LCD first, such that on the top I have sine alpha sine beta. At the bottom left, sine alpha cancel, I have cosine alpha sine beta minus cosine beta sine alpha. Now, it may not be feasible for you, but notice that I can rearrange the product on the denominator into something we get used to. That is, we write sine beta cosine alpha minus cosine beta sine alpha. Do you see that now? I basically switched the order of the product here. That's all I did. Why? Because I want to show you that the denominator now follows sine beta minus alpha, right? But all of a sudden we have the expression on the right-hand side. Therefore, we are done with the proof. Okay, now let me take a break. We come back at 9:10. Okay, let's continue. Let me give you the suggested homework from here in case I didn't give it to you in my lecture. Suggested homework from this 6.3. I would like you to do number 5 to number 49. But also try 53 just for sake of proving. You don't need to memorize that. You don't need to memorize that. Okay, some of them actually quite reinforcement of what we have known. For example, number 37. I just try to reinforce what we have known actually. Number 37, we need to prove tangent x minus pi over 2 equals to negative cotangent x. Now what they wanted us to do is to go from left to right. Okay, to go from left to right using the formulas. Okay, left hand side. I do it fast because I just give you the big sketch of proof. Okay, this is tangent x minus tangent pi over 2 big over. Oh, I don't think that's doable because tangent pi over 2 is undefined, right? That not a good idea. Why tangent pi over 2 is undefined? So we will get stuck there. Okay, let's do another way. Instead of doing it that way, let's make it into sine cosine. That's sine x minus pi over 2 over cosine x minus pi over 2. And then on the top, we will get sine x cosine pi over 2 minus cosine x sine pi over 2 over cosine x cosine pi over 2 plus sine x sine pi over 2. On the top left, cosine pi over 2 is 0 minus cosine x sine pi over 2 is 1 over 0 plus sine x. So this is negative cosine x over sine x. That's negative cotangent x, which is what we have on the right-hand side. Okay, now let me show you the alternative way to look at that. Alternatively, okay, tangent x minus pi over 2. This is just a sketch of proof, okay? That's equals to negative tangent pi over 2 minus x. If I reverse the order of subtraction, that's opposite, right? Is it okay? Maybe I write it this way first. This is equals to tangent of the negative blah. But tangent negative blah is negative tangent blah. And we know this is actually the complement of x, right? Okay, so this is equals to negative cotangent x. What I use there is actually B3, 2. The basic identity is the third group. Actually, no, that's the, the third group, this is the one. This is B42 here. Okay, the third group, the second identity, where tangent pi over 2 minus x equals to cotangent x. That's what I use there. Okay, so this is what we have on the right-hand side. That's the end of the proof. Okay. The one on the left-hand side, this is the standard proof. I believe that's what the textbook wants you to do. Okay, but you can also do it this way. Okay. without using the formulas that we have here at all. Now let's go to 6.4. Let's go to 6.4. We have double angle formulas. That's group 2. Memorize in this order. First one, cosine 2a equals to cosine squared a minus sine squared a. Now that's the first variation. The second variation of the same formula is 2 cosine squared a minus 1. The third variation, cosine 2a equals to 1 minus 2 sine squared a. In my lecture videos, I believe I went over the proof already. Let me just go over that really fast with you. Okay, we know that cosine a plus b equals to cosine a cosine b minus sine a sine b, right? Okay, now, so cosine 2a is basically cosine a plus a. In other words, I replace the b's by a's, right? That's cosine a times cosine a minus sine a sine a. But that's what we have in the first formula. Okay, that's 2, 1, a. The second group, the first formula, the first variation. Now, if I replace sine squared a by 1 minus cosine squared a, that becomes cosine squared a minus 1 plus cosine squared a, which is 2 cosine squared a minus 1. That's the second variation. On the other hand, if I replace the cosine squared a by 1 minus sine squared a, boom, you will get 1 minus 2 sine squared a, right? Which is the third variation. Do I have to memorize all three variations, Thomas? Unfortunately, yes. Okay, because that's one, you will see that becomes one of the key variations that we need later on for half angle formulas. Okay, that becomes one of the key variations for half angle formula. Now, the second formula of this second group is for sine 2a. That is 2 times sine a cosine a. Good news, it's only one variation. How about tangent? Tangent twice an angle is equals to 2 tangent a over 1 minus tangent squared a. Yeah, the formula, the proof is actually straightforward. Basically, for sine 2a, you look at sine a plus b, right? That's sine a cosine b plus cosine a sine b. But then you replace the b by a. Okay, then you get that formula. Likewise, for tangent 2a, you actually do tangent a plus a. Okay, so the same work with what we did here. Okay, those are the sketch of the proof. I will not prove them precisely again. Now, how to use this? how to use this. For example, so I will do the example next door here. Number 3, for example. Okay, secant theta equals to -13/12. Theta is in quadrant 2, between 90 degrees to 180 degrees. Okay. Now let's do the routine first. Okay, the question is find sine, cosine, and tangent of 2 theta. Okay, but before we do that, so the question is find sine 2 theta, cosine 2 theta, tangent 2 theta. Okay, while for me, the main question is actually find 2 theta is in which quadrant. That's what I'm interested in. Okay, now, but let's see. If I want to answer this last question first, theta is between 90 degrees to 180 degrees. So when you double it, it must be between 180 degrees to 360 degrees. In other words, for now, we know 2 theta will be in quadrant 3 or quadrant 4. Okay. Now, if you want to know precisely which quadrant 2 theta located, then doing sine 2 theta will not be of any help, because sine 2 theta in quadrant 3 will be negative. In quadrant 4, it will also be negative. Right? So we know sine 2 theta later on will be negative, and it doesn't tell us any further which quadrant it is located. Because sine of an angle is negative in quadrant 3 and also quadrant 4. Right? So if you want to know if it is in quadrant 3 or quadrant 4, then do cosine or tangent of 2 theta instead. Okay. Now, if you don't want to use this method as one of them, then you need to do 2 of these 3, sine and cosine, or sine and tangent, or cosine and tangent. Okay, see how they behave under the pressure of sine, under the pressure of cosine, or under pressure of tangent. But using the angles, when you double it, you know it is in quadrant 3 or 4, then you just need one of those 2, not 3. Okay, one of those cosine or tangent. Okay, but let's do what they want us to do. Solution. Okay, secant theta is -13/12. Therefore, cosine theta, the reciprocal, -12/13. Now, look at the reference angle and do the right triangle. Cosine is 12/13, so the opposite side is 5. From there, we see sine theta hat is 5/13. In quadrant 2, theta is in quadrant 2, right? So sine theta is still positive, right? Because theta is in quadrant 2. Tangent theta hat is 5/12. So tangent theta in quadrant 2 must be -5/12. Okay, that's the setup. Now then, what is part A? What is sine 2 theta? Sine 2 theta is equals to 2 sine theta cosine theta. That is 2 times 5/13 cosine theta -12/13. That's -120/169. As I said earlier, if you want to know which quadrant angle 2 theta located, Sine 2 theta will not tell you anything more because we know 2 theta from here, 2 theta will be quadrant 3 or quadrant 4. But sine 2 theta, as we expect, will be negative, and we still cannot tell is that in quadrant 3 or quadrant 4. Because 2 theta in quadrant 3 will be negative, in quadrant 4 will also be negative. So far we cannot say anything. Okay? So far we cannot say anything about where 2 theta are located. Now let's do the cosine. So part B, how about cosine 2 theta? This is 2 cosine squared theta minus 1. Thomas, there are 3 formulas. How do I know which formula to use? There are 3 formulas for cosine 2 theta. How do I know which formulas I use? Actually, you can use all 3. You will get the same result. But why, Thomas, you decide to use the second variation instead of the first or the third? Well, because I can easily find cosine theta without much computation, right? I don't even need this triangle to get cosine theta. Okay. That's why I use the second variation, in which I only need the value of cosine theta. Okay, that's my explanation. But it doesn't mean you can only use the second variation in this case. No, you can use other variation also. Okay, but the closest one, the easiest one we can do is this one. This is 2 times negative 12 over 13 being squared minus 1. That is 2 times 144 over 169 minus, let me do LCD at the same time. So this is 288 minus 169 over 169. What's that? Hmm. 169 at the bottom. And then 119 at the top. Is that right? Okay. And at this point, we have seen the cosine 2 theta is positive. So 2 theta must be in quadrant 4. Okay, to be more precise, cosine is positive in quadrant 1 and quadrant 4. Right? Okay, but together with what we see here, together with what we see there, then we conclude 2 theta must be in quadrant 4. Okay, from cosine 2 theta point of view, it's 1 or 4. From doubling the angle point of view, it's 3 or 4. So it must be in quadrant 4. Okay. Now with that said, then, as we expect, when we compute the tangent to theta later on, then tangent to theta is supposed to be negative. Supposed to be negative. Because otherwise it will contradict with what we have known so far, that 2 theta is in quadrant 4. Okay, this is 2 tangent theta over 1 minus tangent squared theta. This is 2 times, what is tangent theta? Negative 5 over 12. Negative 5 over 12 over 1 minus negative 5 over 12 squared. That is negative 10 over 12 over 1 minus 25 over 144. Multiply the top and the bottom by 144, the LCD. I will get negative 120 over 144 minus 25. Okay, this is negative 120 over 119. As we expect, because 2 theta is in quadrant 4, then the value should be negative. However, part C here can also be done easily, tangent to theta alternatively. Tangent to theta can be done by looking at the sine 2 theta over cosine 2 theta, which both of them we already have. Cosine 2 theta is, sine 2 theta is negative 120 over 119. Oh, no, it's not 169. Yeah, 169. And cosine 2 theta is 119 over 169. I think this is an easier way to find the tangent since we already have the sine and cosine. Okay. Now that's for double angle formulas. How about half angle formula? Before I go to half angle formula, I need to insert here something I call something we call power reduction formula. Power reduction formula. This is the bridge between group 2 double angle formulas and group 3 half angle formula. Now, the formula is so easy and so obvious actually, such that we don't even put them into one of the group. Like we have group 1, which is, if we look back, group 1 is the addition formulas, right? Addition and subtraction formulas. Group 2 is double angle. Okay, group 3 later on will be half angles formula. Okay, now between group 2 and group 3, we have power reduction formula. Now, power reduction formula, the first one is cosine squared A equals to 1 plus cosine 2A over 2. Where it comes from? Remember I said it is so easy such that they don't even put it in a group, okay? Because it's just a direct computation from there. If you solve for cosine squared A, right? You add 1 divided by 2, right? Mickey Mouse. Okay. Now, the second power reduction formula is for sine squared A. Remember I said earlier you need to memorize those variations also? Now, it is because of this reason. Okay, because power reduction formula actually coming from there. Okay, this is 1 minus cosine 2A over 2. Now, consequently, then, tangent squared A is the ratio of sine squared A over cosine squared A, 1 minus cosine 2A over 1 plus cosine 2A. Okay, that's power reduction formula. Our textbook seems like not emphasizing that much about power reduction formula until much later. But I want you to realize that this power reduction formula is very powerful and important. So even though I don't put it in a certain group, not group 1, not group 2, not group 3, we just call that power reduction formula. But this becomes important for example, if I ask you graph, okay, y equals to, let's say 3 plus 2 sine squared x. Can you graph that? Oh, Thomas, we never graph sine squared x. We never graph sine squared x, but we know what sine squared x right now. This is sine squared x is 1 minus cosine of double angle over 2. Do you see that? Okay, so this is 3 plus 1 minus cosine 2 theta. This, I'm sorry, 2x, which is now 4 minus cosine 2x. Now from there you can do, the center is 4, the amplitude is 1. Okay, the period is 2 pi over 2, which is pi, right? Now on Thursday, you need to know this though. Okay, you need to know how to graph this, right? Okay, the phase shift is 0. You don't shift that anywhere. Okay, so when I graph that into the 2 by 4 window, the center is 4, maximum is 5, the minimum is 3, which means this graph has no x-intercept, right? Okay, this is 0, the period is pi, so 0 plus pi is pi, this is pi over 2, pi over 4, this is 3 pi over 4. That's negative cosine, so the graph will look like from the bottom, negative cosine, going up, going up, going down, going down. Make sure you curve it. Okay, that's what it looks like. Now the thing is, our textbook did not emphasize that part. Okay, now that's for power reduction formula. Even though that's not one of the group, I need you to memorize that. Let me box it. So this is something we learned from group 2. Something we learned from group 2.5, if you want to call that power reduction formula as group 2.5. Now group 3, half angle formula. The first one, cosine A over 2 is equals to plus minus square root of 1 plus cosine A over 2. You know what? Instead of using A, let me use theta. Let me use theta. Okay. The second one for the sine, sine theta over 2 equals to plus minus square root of 1 minus cosine theta over 2. So over 2 is included into the square root, okay? And 3a tangent theta over 2 is plus minus square root of 1 minus cosine theta over 1 plus cosine theta. Okay, the proof actually coming from power reduction formula. We have known that cosine squared A is equals to 1 plus cosine 2A over 2, right? If I substitute 2A to be theta, then this becomes cosine squared theta over 2 equals to 1 plus cosine theta over 2. Does it make sense? And then apply the square root. Therefore, you are done with the formulas. Where the plus minus is adjusted, plus minus is adjusted with the quadrant, where theta over 2 located. Okay. Now the thing is, the third formula has two other variations which are better. Okay. The second variation of tangent half angle is 1 minus sine theta over cosine theta. The third variation, which is equivalent, like of these three formulas, the last two here, the last two are equally important. Okay, this is cosine theta over, I'm sorry, it should be sine theta. It should be sine theta. There's the same sine theta over 1 plus cosine theta. Now, the nice thing about the last two formulas, you don't need to worry about the quadrant. You don't need to worry about the quadrant, therefore decide the plus minus. Okay, these three formulas here requires you to know which quadrant theta over 2 located first. Okay, you need to know where theta over 2 located first so that you can tell which quadrant, you can tell the plus minus sign. Now, the good thing with formula 3b and 3c is you don't need to. You don't need to. Okay. Now, how do we use this formula? One of them is to find out what is 15 degrees. That's half of 30 degrees, right? 15 degrees is half of 30 degrees. So how do we use this to find, for example, cosine 15 degrees? Now, cosine 15 degrees is in quadrant 1, so we will use the positive branch. Okay, maybe I write it this way. Cosine 15 degrees is cosine 30 degrees over 2. So that is quadrant 1, so it's positive, square root of 1 plus cosine 30 degrees over 2. Okay, then we compute. This is square root of 1 plus radical 3 over 2 over 2. Multiply the top and the bottom by 2 inside the square root will give me square root of 2 plus radical 3 over 4. Which is equal to 1/2 radical 2 plus radical 3 over 2. Okay. The 4 just becomes a 2. Yes, because the 4 here is inside the square root. When I bring it out, it becomes just 2 without the square root. Right? Okay. Now it is positive. This is positive. Likewise for the sine, that will also be positive. Now let me show you how to work on the tangent. Tangent 15 degrees, that's tangent 30 degrees over 2. Now suppose I use formula number 3, group 3, number 3, the second variation. the second variation, which is 1 minus cosine 30 degrees over sine 30 degrees. This will be 1 minus, what is cosine 30 degrees? Square root of 3 over 2 over sine 30 degrees, 1/2. Multiply the top and the bottom by 2. I will get 2 minus radical 3, done, over 1. Now compare that E to if I use formula 3a. Okay, tangent 30 degrees over 2. Oh, it is quadrant 1. So it is the positive. 1 minus cosine 30 degrees over 1 plus cosine 30 degrees. So you see that I decide the plus minus here by first knowing that 15 degrees is in quadrant 1. Okay, that's how I know it's plus, right? Notice that I didn't do that here. I didn't do it there. And I don't need to do it there. I just go ahead with the computation. So that's the benefit of formula 33b and 33c compared to formula 33a. Okay, 33a, I still need to know which quadrant it is located. That's first. And second, take a look on the computation inside the square root. That's messy. So 1 minus radical 3 over 2, 1 plus radical 3 over 2 under square root. Now I will multiply the top and the bottom by 2 inside the square root, such that we have square root of 2 minus radical 3 over 2 plus radical 3. But I still need to rationalize this though. Right? I will multiply by the conjugate of the denominator inside the square root. So I hope you see how busy I get. So on the top, I get 2 minus square root of 3 being square. At the bottom, I have 4 minus 3, which is 1. So that's 2 minus square root of 3 over 1. Right? You see that? The square root cancels the square here. So I get that only. Okay. 4 minus 3 is 1, under square root is just 1. But, well, you see, like I basically get BC. Okay. That shows you how much formula 33b and 33c more superior than formula 33a. Okay. In fact, we don't really use formula 33a anymore. Okay. We don't use formula 33a anymore. Now, what happens if, let's say, the angle is not in quadrant 1, let's say 75 degrees. Notice that 75 degrees, we computed earlier. 75 degrees is one way to see that is 45 degrees plus 30 degrees, right? Okay. But we can also compute 75 degrees using half angles. So suppose I want to know what is, let's say, cosine 75 degrees. Cosine 75 degrees is in quadrant 2, so it has to be negative. And then square root of 1 plus cosine 150 degrees over 2. Okay, so I know this is negative because 75 degrees is in quadrant 2. I need to predetermine which quadrant the angle located. From there, then I know the sign in front of the square root. This is equal to, so let me partition this a little bit. Okay, this is equal to negative square root of 1 plus negative radical 3 over 2 over 2. Multiply the top and the bottom by radical 2. I'm sorry, by 2. Then I will get negative square root of 2 minus radical 3 over 4. Cosine 75 degrees is negative, yes, because 75, oh, hold on. No, it's positive, huh? Oh, my bad. You're right, duh. I have 115 in mind. Sorry. No, so I already make mistake here. 75 degrees not in quadrant 2. Thank you. Oh, duh, I have 105 degrees in mind. So no, this is wrong. This is quadrant 1. So this is positive. 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 Is it okay now? Okay. Yeah. Thank you very much. Yeah. Thank you very much. It should be positive. What I had in mind was like, duh, what am I doing? Cosine, thanks. That's a big correction, by the way. Cosine 105 degrees, for example. That is in quadrant 2, right? Okay, cosine 105 degrees is in quadrant 2, but 105 degrees is 210 degrees over 2. Even though you can also see 105 degrees as 60 degrees plus 45 degrees, right? You can also do that. Now, this is equals to negative square root of 1 plus cosine 210 degrees over 2. Like that. Okay, that's what I meant earlier. Okay, and then so on and so forth. Now, let's go on. Suppose we have number 13. Number 13. Cosine beta is 9 over 41. And beta is in quadrant 4. Find the exact value of tangent beta over 2. The exact value. Solution. We need to first find beta over 2 is in which quadrant. Beta is in quadrant 4, which implies beta is between 270 degrees to 360 degrees. Now beta over 2, therefore, we divide that by 2. Right, so b over 2 is between 135 to 180. Well, it means beta over 2 is between 90 degrees to 180 degrees. Is it right? I just want to say that beta over 2 therefore is in quadrant 2.
So expensive. Oh.
Now, because beta over 2 is in quadrant 2, then tangent of beta over 2, actually, the setup's supposed to be like this. So from there, we get this. Now tangent beta over 2 will be negative. Okay, so if you use that square root formula, if you use B3A, then it will be negative square root of 1 minus cosine beta over 1 plus cosine beta. Okay, but no, I don't think I want to do that one. I don't want to use that formula. It's kind of a lot of headache. However, on the other hand, I need to draw the triangle, right? Because beta is not in quadrant 1, I need to use the reference angle. For cosine, that's 9 here, 41 here. What will this be? What is 41 squared minus 9 squared under square root? That's square root of 50 times 32. 40. Do you know what I'm doing here? Do you know what I'm doing there? How do I get that 50? How do I get that 32? You want to do mental math? This is mental math. That's right. We use difference of squares, right? A squared minus b squared is a plus b times a minus b. That's what I did there. And then when I look at this, oh, you know what? I can make that 50 multiplied by 2 becomes 100, but then the 32 I divide by 2. So that's how I see this is 10 times 4. You see? Okay. So I do this without calculator. In fact, it's actually faster than your calculator. Why? By the time you grab your calculator from your bag, I'm done with the computation. Okay, now then coming back here. So from there we see sine, actually I need cosine. Cosine, no, I have the cosine. I need the sine, that's right. I have the cosine, I need the sine. So sine beta will be, sine beta hat will be 40 over 41, but beta is in quadrant 4, so sine beta should be negative. Now then go back to the tangent. Tangent beta over 2 is 1 minus cosine beta, which we are given, over sine beta. Okay, this is 1 minus 9 over 41 over negative 40 over 41. Multiply the top and the bottom by 41. I get 41 minus 9 over negative 40. Reduced by 8, that's negative 4/5. As we expect, this angle beta over 2 is in quadrant 2, therefore the tangent has to be negative. Okay, now some more proving. I will be looking at number 17 to number 27. Okay, see with me. Number 17 to number 27. Choose 2 questions that you want me to do. Number 17 to number 27. Let me do number 25 maybe, or number 21 first. Okay, let's see. There's a number 26. Okay, I will do number 26. Let me do number 21 first. Number 21, sine squared of x over 2 equals to sine squared x over 2 times 1 plus cosine x. I think I will prove from left to right. Sine squared x over 2. Oh, what am I doing? Left to right, left hand side. That's equals to sine squared x over 2. Okay, I think I will use power reduction formula. I think, but this means this is equal to power reduction formulas is sine 2a equals to 1 minus cosine 2a over 2. Right? Okay, so this will be 1 minus cosine of 2 times x over 2 big over 2. Right, so that's 1 minus cosine x. 1 minus cosine x over 2. But it seems like I'm going nowhere. I don't get what I want. Even though I think this is very simple. This is the simplest possible. Multiple. Both 1 minus cosine x. Oh, you know what? I know what to do right now. Okay. I know what to do right now. I see at the bottom, I already have the 2. Right? I just need 1 plus cosine x. See, if I multiply the top and the bottom by 1 minus cosine x, so I mean 1 plus cosine x, it happens to be the conjugate on the top, I will get 1 minus cosine squared x. Okay, let me show you. So what I will do next is multiply the top and the bottom by multiply the top and the bottom by 1 plus cosine x. So that will give me 1 minus cosine squared x over 2 times 1 plus cosine x. But on the top, that is sine squared x. Which is our right-hand side. That's the end of the proof. Okay. And I use this actually here. Okay, let me do number 26. Number 26. Sine proof, sine 4t equals to 4 sine t cosine t times 1 minus 2 sine square t. Oh, okay. But you know we will start from the left-hand side. Why? Because that's multiple angle. Correct? Left-hand side, which is sine 4t that is sine twice 2t. So this is 2 sine 2t cosine 2t. Oh, that's straightforward because sine 2t is 2 sine t cosine t. Cosine 2t, one of the variation is 1 minus 2 sine squared t. Hey, we are done. Okay, so I actually use this formula. From here to here, I use a double angle, the second formula, double angle, the second formula, double angle, the third formula, the third variation. So this is the right-hand side. That's the end of the proof. Okay, by the way, what are important? Actually, question like number 29. Number 29 is important. Yeah, number 29 is important. Do you notice that's actually power reduction? Number 29. Okay, reduce, that's actually proving the power to 1 with multiple angle. Okay, proof that sine to the 4t is equal to 3 over 8 minus 1/2 cosine 2t plus 1/8 cosine 4t. Okay, I say this is important. You don't need to memorize this, but you need to know how to do this. Okay, this is important for your calculus 2 later on. Important for Calc 2. Why? In Calc 2, one of the things you need to learn or to do is to integrate sine to the 4th t dt. However, this is not doable directly. This is not doable directly. This has to be changed into, you need to reduce the power. You need to reduce the power. So later on you will see this is equals to 1/8 integral 3 minus 4 cosine 2 theta 2t plus cosine 4t dt. Then you can integrate this. Okay, now the thing is, you know, I'm currently teaching calculus 2 also, right? So I have too many students don't know how to go from here to here. Too many students. Because the time from they took trigonometry, at West LA College, trigonometry is prerequisite for pre-calculus, right? So by the time they finish their trigonometry, until they start working on this in calculus 2, there were at least 6 months already passed, at least usually 1 year. So they already forgot how to do this, and their trigonometry teacher usually don't ask them to do this. Okay, but I do. Why? Because I teach calculus 2, so I know in your pre-calculus class here, one of the questions you need to encounter is this: how to reduce the exponent. Okay, from degree of 4 down to degree of 1, the power of 1, but with multiple angle. Okay, so get ready with sine to the 4th, cosine to the 4th. Okay, sine cube, cosine cube. Is it okay? Sine cube is actually not too hard. I think I will do that later. Do we have that kind of question here? No, I do it later. Yeah, let me do this one first. Proof. Even though the right-hand side is more complicated, but it's basically coming from left-hand side being reduced. This is sine to the fourth t. That is sine squared t being squared. Now then we use power reduction. This is 1 minus cosine 2t over 2 being squared. That is 1/4. I FOIL that. Okay. Now then, this is okay. Cosine 2t is okay. The power already 1. Cosine squared 2t is not okay. Now then, let me multiply that 1/4 in. So I get 1/4 minus 1/2 cosine 2t plus 1/8 plus cosine 4t 1/8. Now 1/8 plus 1/4, that's 3/8. Which is our right-hand side. Therefore, that's the end of the proof. Okay, there are more proofing to be done there. In the last 10 minutes, let me do solving equations. In the last 10 minutes, let me do solving equations. Oh, I have chat coming. Is it 1 plus 3t over 8? Did I write 3? No, 4t over 9. The last one here? This is 8, 1 over 8. Yeah, 1/4 times 2. 1/4 times 1/8 is 1/8. I'm sorry, 1/4 times 1/2 is 1/8. The 3/8 here. The 3/8 here coming from 1/4 plus 1/8. Okay, let me slow down. Let me erase the coloring first. So what I did was I distribute this 1/4 with 1/2. That gives me 1/8, right? And then 1/4 with this give me this. Is it okay? Okay. Yeah. Now, one last question before we go on, before I end the class. Pick one question between number 43 to number 51. Number 49, why not? Number 49. Actually, I like this question number 49 because I would like to show you two different ways to do this problem. Sine u over 2 plus cosine u equals to 1. Solve. Okay, the first method, method number 1. What I will do is I will isolate the sine and then square it. But somewhere in between, because I square both sides, then you know at the end, later on, you need to check your final answer against extraneous solution. Okay, so what happened here? I square both sides. Why do you square both sides, Thomas? Because the original formula for sine half angle is plus minus square root of 1 minus cosine u over 2. Do you remember that? Okay. So I don't like the plus minus, that's the thing. However, I can get rid of that by squaring both sides. Okay, I will get rid of that by squaring both sides. So this becomes 1 minus cosine u over 2. And on the right-hand side, I have 1 minus cosine u being squared. Okay, now because this is quadratic, you can FOIL if you like. You can FOIL if you like. The way I see is like you actually have common factor, 1 minus cosine u as common factor. That's the way I see. So what I think I will do is, I will do this kind of strange manipulation. I know it's strange. 0 equals to 1 minus cosine u squared minus 1 minus cosine u over 2. And I factor the common factor 1 minus cosine u. Can you see that? So I take the common factor 1 minus cosine u out. Okay, that way I don't need to FOIL and then factor. Okay, but then from there I see cosine u equals to 1. And here we get cosine u equals to 1/2, right? So we have these angles. Cosine u equals to 1 means u equals to 0. Cosine u equals to 1/2 means u equals to pi over 3, or quadrant 4, 5 pi over 3. But remember earlier we square both sides, so we need to check the solution against the original equation. Check. So u equals to 0. Sine for u equals to 0, sine 0 over 2 plus cosine 0, is it equals to 1? This is 0 plus 1, is it equals to 1? 1 equals to 1, check. How about when u equals to pi over 3? Now sine pi over 3 over 2 plus cosine pi over 3, is it 1? That's sine pi over 6 plus cosine pi over 3, is it 1? This is 1/2. That's another 1/2. So it's a check, huh? The third one, how about when u equals to 5 pi over 3? So sine 5 pi over 3 over 2 plus cosine 5 pi over 3, is it equals to 1? This is sine 5 pi over 6, that's quadrant 2, so it is positive. Cosine 5 pi over 3, That's quadrant 4. That's also 1/2. Oh, all of the solutions are correct here. So all of them okay. So u equals to 0, u equals to pi over 3, u equals to 5 pi over 3. But see, I spent much time in checking, or at least a couple minutes, right? Another way to solve this problem, something even our textbook don't show you, is I do substitution. The second way, let u over 2 equals to x. 5 pi over 3 is not correct. Why? Let's see. Let's see. Cosine 5 pi over 3, that's quadrant 4, right? Reference angle pi over 3. So that's 1/2. 5 pi over 3 divided by 2 is 5 pi over 6. That's quadrant 2. Sine in quadrant 2 is positive. So, yeah, I see that's correct. I see that's correct. Okay, but we still need to check. The thing is like, we still need to check. Okay, if it is not correct, then just cancel it out. But according to my computation here, that's correct. So all three happens to be the solutions. Okay, now the second method, I have only 1 minute left, but let me show you the second method. So let u over 2 equals to x. Cosine 5 pi over 3 is negative 1/2. I don't think so. How do you get that? Cosine 5 pi over 3. That's quadrant 4, right? So quadrant 4 cosine is positive. And the reference angle is pi over 3. Yeah, cosine in quadrant 4 is positive. Okay, yeah. Okay. Oh, that's okay. That's okay. You know, I make that mistakes too before. Okay, but I want to focus on the last method here. Okay, so instead of dealing with half angle, I do substitution such that we end up with double angle. You see? Now 5 pi over 6 is in quadrant 2. 5 pi over 6 is in quadrant 2 because it's less than 1. It's less than 1 pi. Right? Oh, that's okay. Yeah. We still need to get used to it. Okay. Now I do this substitution coming back here. So my equation that I need to solve now becomes sine u plus sine x plus cosine 2x equals to 1. Okay. Now then sine x plus, I use the third variation, 1 minus 2 sine squared x. Why? Because I have sine x on the other side. So I change everything to sine. And the nice thing is the 1 cancels anyway after that. So I can factor sine x out, 1 minus 2 sine x. Notice that I don't square both sides here. So whatever answer I get will be the answer. Okay, so sine x equals to 0, which means x equals to 0. Sine x equals to 1/2. So x is pi over 6 or 5 pi over 6. Is it right? But that's x. We need the u. U equals to 2x. u equals to 2 times pi over 6, that's pi over 3. U equals to 2 times 5 pi over 6, that's 5 pi over 3. No checking necessary. You see that? Okay. I don't need to check, but I get the same answer. Okay, so it may be better to avoid the duality of that half angle. Therefore, I need to square it. I am forced to square it. And after I square it, I need to check later on. Instead of going to that route, okay, instead of going through that route, I make it double angle first. So I substitute the half angle becomes, I call that x. Okay, so the one that I don't have, the actual u becomes 2x. That's how you change a half angle question becomes double angle questions. Okay, now double angle question, you don't need to square any step in between. Okay, at least that's what we see, right? And therefore, we don't need to check any answer we have at the end. That's the nice thing about the second method. Okay, now I will stop here. Your suggested homework from this 6.4 will be from number 1 to number 51. Okay, now don't study this 6.3, 6.4 until you are done with your test on Thursday. Okay, see you then. That's for today.